Hello. I just want to complement what we discussed in the previous video. We had a problem similar to this one. Okay, I'm just going to try to graph it the best as possible way. We had some linear constraint over here, another linear constraint over there. Okay. Remember that this problem had some gradient vector of my objective function like this, okay, and the gradients of constraints were pretty much like this. When I told you guys that we have a convex cone, that's a kind of a basic idea when we talk about convex optimization. That means the following. If I multiply, let's call this vector as v1 and this vector as v2, you can notice that if I multiply alpha 1 by v1 plus alpha 2 by v2, I will have a linear combination to form my main vector over here, which is the gradient of my objective function. Okay, so of course that's the same as, just imagine as having an axis over here, multiplying of course the length of this vector for a given alpha 1 and this for some alpha 2. I'm going to try the best of, okay, my drawing is not that good, but anyway. If you think about this, all this region, it forms a convex set. That's why we call it like a convex cone. Why a convex set? Because if I take any point here, okay, and I combine with any other point here using a linear function, the linear function lies inside my feasible set. So I can combine like this, I can combine like this, I can have some point like this, or here maybe, or here, like this. And that's why actually those are called our Karush-Tucker multipliers, and those must be greater than or equal to 0. Okay. There is something else over here that I want to share with you as well. Again, I think you guys remember that I told you that if I had, I just showed you like a reference in one of those videos as well. If I have, of course, a minimization problem, that's how it works. If I have a maximization problem, you know what's going to happen with this vector, this gradient vector here. It will be actually on the other side like this. This is why we have to use the minus sign for maximization problems in our Lagrangians. And that's why we use the plus sign in our minimization problems when writing Lagrangians. It will affect on the sign of this gradient vector for my objective function. You can also think on the opposite. I can change the sign of those constraints to fit my problem, okay, like this. So I will have a convex cone to the other side. Both are okay if you think in one way or the other. So for instance, remember, consider I have like some objective function f of x that I want to, for example, maximize. And I am subject to some constraint gi. That's some constraint that I must be like greater than or equal to 0, for instance. If this is a maximization problem, I should write my Lagrangian, of course, in terms of my f of x minus some Lagrange multiplier multiplied by my GI solved for the equality equals 0. Okay, just making it equal 0. That's okay. If I have on the other side, if I had like a minimization of some, could be the same f of x, subject to some GI over here as well, let's consider it's also greater than or equals to 0. What should I do? I should just solve just create my Lagrangian function in terms of f of x, and here I will use the plus sign to multiply my Cauchy-Tucker multipliers by GI solved for the equality as well. This sign is the reason for which we use those signs is exactly to sustain the gradient vector of our objective function inside the convex cone. If you look at this, you can probably see like this. Okay, if my function, when I find the derivative of the Lagrangian in terms of this x, this gradient will be on the opposite side, on the reflected side of my convex cone. When I multiply by minus something, what I'm going to do here is exactly inverting my constraints like this, reflecting my constraints like this, and verifying if when this vector becomes a linear combination of my constraints, exactly like this. Okay, and of course, if I have a minimization problem like this, there is no need. I can just sum up, because the solution will automatically or naturally lie inside my convex cone like this. That's quite interesting. That's actually the reason. You probably guys, now I invite you guys to go back to one of the videos I did like 3 videos ago or 4 videos ago. I was using minus here as well. I want you guys to do something for me. You know that for that minimization I solved with you guys, I was using minus here, but instead of minus, please plug negative and solve for it. You are going to notice, and that's an exercise as homework for this class. After doing that, you are going to notice something quite interesting. Instead of obtaining like C transposed X, you're going to obtain minus C transposed. You know why that's going to be inverted? That's actually is going to be inverted to make this gradient function, this gradient vector of my objective function, it's going to bring this vector inside my convex cone. Please solve that and bring your questions to our office hours. Okay? See you guys.